Chapter 10 is all about liquids and solids and their properties more in depth. In the preceding chapter, we studied the physical properties of gases, and one of the major observations was that all gases behave pretty much alike regardless of their chemical makeup. However, when we compare substances in their liquid and solid states, the situation is quite different. When a substance is a liquid or a solid, its particles are packed closely together, and the forces between them, which are called intermolecular forces, are quite strong. Chemical composition and molecular structure play an important role in determining the strengths of different intermolecular forces, and this causes different substances to behave quite differently from each other when they are liquids or solids. It's first important to compare intramolecular forces to intermolecular forces. Intramolecular forces are the chemical bonds that hold atoms together. These are also known as bonding forces. The two major types of bonding forces that we've studied so far are ionic and covalent bonding. We can consider two examples, hydrogen chloride and sodium chloride. If we look at hydrogen chloride, we have a covalent bond between hydrogen and chlorine. This covalent bond is a single bond comprised of two electrons. We have two nonmetals bonded together. Therefore, HCl is a molecule. Hydrogen and chlorine also have two different electronegativities, with chlorine being more electronegative. Therefore, the chlorine will develop a partial negative charge, whereas the hydrogen will develop a partial positive charge. Sodium chloride, on the other hand, is an ionic compound made up of a metal and a nonmetal. There are no partial charges in something like sodium chloride. There are full charges. The sodium loses its one valence electron to develop a +1 charge, and the chlorine gains that one valence electron that sodium gave up and develops a full negative charge. The interaction of positive ions with negative ions represents an ionic bond. We'll see that the strengths of the intramolecular forces, or the bonding forces, are what determines the chemical properties of various substances, whereas intermolecular forces, which is going to be the focus of this chapter, those determine a substance's physical properties. Intermolecular forces, often abbreviated IMFs, are the forces that occur between molecules. So if we look at this example, imagine you have a sample of hydrogen chloride gas. Hydrogen chloride will have some forces that are occurring between each of the individual hydrogen chloride molecules. Those represent the intermolecular forces of attraction. IMFs are always weaker than the bonding forces. So no intermolecular force is stronger than a covalent or an ionic bond. They can often determine the state of matter that something occurs in. So different IMFs can determine if something ends up being a solid, liquid, or a gas. Properties of solids and liquids will depend upon the types of intermolecular forces present. There are 4 different types of intermolecular forces that we'll study in this chapter. Well, first we'll look at dipole-dipole interactions, and then hydrogen bonding, which is a special type of dipole-dipole interaction, London dispersion forces, sometimes abbreviated LDFs, and ion-dipole forces. Dipole-dipole interactions are the forces that occur between molecules when a partially positive end of a molecule interacts with a partially negative end of another molecule. Dipole-dipole interactions only occur in polar molecules. So we have to remember how to be able to determine if a molecule is polar or nonpolar based upon its VSEPR shape. Imagine our sample of hydrogen chloride gas. Hydrogen has a less electronegativity than chlorine, so it develops a partial positive charge. Chlorine is more electronegative, so it develops a partial negative charge. If we consider how another molecule of hydrogen chloride is going to want to line up next to our first molecule, the positive charge, the partial positive charge on another hydrogen is going to want to be near the partial negative of chlorine, because opposite charges are going to be favored, whereas like charges are going to repel. So the partial positive on hydrogen will pair up with the partial negative on chlorine, and this will continue. The partial negative on another chlorine will have an interaction with a partially charged hydrogen on another molecule, and this will continue. So we can think of our polar molecule almost like a small magnet. The small magnets are going to orient themselves so that the positives and the negatives line up. Positive next to a negative, positive next to a negative. And the whole sample of our hydrogen chloride gas will continue with this repeating pattern. This net attraction that we see between polar molecules is referred to as dipole-dipole interactions or dipole-dipole attractions. It's generally much weaker than a covalent bond. It's only about 1% as strong as a covalent bond. Dipole-dipole attractions fall rapidly with distance. Dipole-dipole interactions are relatively weak, and this is because the charges on the molecules are only partial charges. So in our molecule, we don't have a full positive and a full negative on our hydrogen and chlorine. We have partial charges because they're sharing the electrons within that covalent bond. And recall that the more electronegative atom is pulling the electrons within that bond towards itself more. So chlorine is more electron greedy. We can only have these dipole-dipole interactions in molecules that are polar in the first place. If the molecule is nonpolar, it will not have any dipole-dipole interactions. The strengths of intermolecular forces between molecules affect properties such as boiling points and melting points. As the polarity of a molecule increases, the boiling points and melting points also increase. Let's compare two examples. Butane, C4H10, this is what's in lighter fluid, to acetone, C3H6O, which is in nail polish remover. Let's determine which molecule would have the greater boiling point based upon the polarity of the molecule. Let's compare the structures of butane and acetone. Butane is C4H10. This is a hydrocarbon. It's an organic compound that is composed entirely of carbon and hydrogen. Carbon-carbon bonds are going to be nonpolar, and carbon-hydrogen bonds have such a small difference in electronegativity that essentially a carbon-hydrogen bond is also a nonpolar bond. Since our molecule has a tetrahedral arrangement around each carbon center and it's totally symmetrical, and it's also composed entirely of carbon and hydrogen bonds, which are all nonpolar, overall the molecule is going to be nonpolar. Comparing this to acetone, C3H6O, this is going to be a polar molecule. The polarity comes from the fact that we have a carbon double bonded to an oxygen. The oxygen is more electronegative and will develop a partial negative charge, and the carbon bonded to that oxygen will develop a partial positive charge. So the electrons are being pulled towards that oxygen atom. Above, we see an electrostatic potential chart. Where it's red, that shows where the electron density lives. So most of the electron density in the acetone molecule is sitting on the oxygen atom. Also notice that butane and acetone both have the same molar mass. They both have a molar mass of about 58 grams per mole. This makes them good to compare the physical properties because sometimes the size of a molecule can impact the boiling point and melting point as well. Notice in butane, which is nonpolar, the boiling point is negative 0.5 degrees Celsius. This means that butane is actually a gas at room temperature. Versus acetone, which is a polar molecule, it has a boiling point of 56.2 degrees Celsius. So the intermolecular forces between our polar acetone must cause the boiling point of this molecule to be much greater than that of butane, which is a nonpolar molecule. Acetone contains dipole-dipole interactions between its molecules, whereas our nonpolar butane molecule does not have dipole-dipole interactions. Butane will have its own type of intermolecular forces between it, but we haven't discussed those just yet. It's important to be able to determine if a molecule is polar or nonpolar. Let's try another example. Arrange the following in order of increasing dipole-dipole interaction, or in other words, increasing polarity: HCl, HBr, and HI. We also have off to the right a chart of the electronegativities of the elements. If we think about what each of these bonds is going to look like, they're each going to be a polar covalent bond, where hydrogen is bonded to some electronegative atom. In each case, chlorine, bromine, and iodine are more electronegative than hydrogen, so they're going to develop the partial negative charge. Hydrogen is less electronegative, so it will develop the partial positive charge. If we think about what the difference in electronegativity between the two elements are within the bond, we can rank the polarity of them. Chlorine is going to be more electronegative, and it has an electronegativity of 3.0. Hydrogen is less electronegative, and it has an electronegativity of 2.1. If we subtract the difference, we'll end up with 0.9 for HCl. And this is kind of an indication of the polarity of the bond. The greater the difference in the electronegativity between the two elements, the more polar the bond is. The more polar the bond is, the stronger the dipole-dipole interactions can be. Difference in electronegativity between hydrogen and bromine. Bromine is 2.8 minus hydrogen, which is 2.1. So our delta En will be 0.7. And for HI, the delta En, iodine is 2.5 minus 2.1 for hydrogen will be 0.4. So we can see that HCl is going to be the most polar, and HI is going to be the least polar. The most polar molecule is going to have the strongest intermolecular forces between it. So those dipole-dipole interactions are going to be stronger in HCl than they are in HBr. The dipole-dipole interactions in HBr will be stronger than they are in HI. So ranking our three molecules in order of increasing dipole-dipole interaction, we'll have HI with the weakest, followed by HBr in the middle, and then HCl will be the strongest dipole-dipole interactions. The second type of intermolecular force that we'll discuss is called hydrogen bonding. Hydrogen bonding is a special kind of dipole-dipole interaction. It's also a very important kind. It occurs when hydrogen is covalently bonded to a very small, highly electronegative atom. Particularly, hydrogen must be bonded to oxygen, nitrogen, or fluorine. So in order to have a hydrogen bond, we have to have an HO bond in our molecule, an HN bond, or an HF bond. Oxygen, nitrogen, and fluorine are three of the most electronegative atoms on the periodic table, so those atoms will develop a partial negative charge. Hydrogen is more electropositive and will develop a partial positive charge in each case. It's similar to a dipole-dipole interaction, but it's much stronger. The electrons within the covalent bond are being pulled very strongly towards the oxygen, nitrogen, or fluorine, creating a much stronger dipole-dipole interaction. Also, this occurs because oxygen, nitrogen, and fluorine are all very small atoms. Because of the small size of these atoms, the charges are highly concentrated. This allows the dipole, the positive end of one dipole, to get really close to the negative end of another because they are so small compared to other dipole-dipole interactions. All of these factors add up to make hydrogen bonding a special type of dipole-dipole interaction. It also occurs in polar molecules, just like regular dipole-dipole interactions. No polar molecule, no hydrogen bond. And if we don't have hydrogen specifically bonded to one of those three elements, we will not have a hydrogen bond type dipole-dipole interaction either. If we imagine water, H2O, it has an AX2E2 bent structure. and it can actually form multiple hydrogen bonds per molecule. The partial positive on a hydrogen will interact with the partial negative on an oxygen in another molecule. This is considered a hydrogen bond between those two molecules. That same oxygen can interact with another partially charged hydrogen on a different molecule and form another hydrogen bond. This pattern will keep repeating itself, and the hydrogen bonding between something like water actually allows for water to have some interesting properties as well. Typically, a hydrogen bond is about 5 to 10 times stronger than other dipole-dipole interactions. If a molecule contains hydrogen bonding, this will have an impact on the observed boiling point or melting point. Water, H2O, if we look at the difference in electronegativity between oxygen and hydrogen, oxygen has an electronegativity of 3.5. Hydrogen has an electronegativity of 2.1, giving us a difference of 1.4. Sulfur and selenium are in group 6A below oxygen. They won't form hydrogen bonds, but they will form dipole-dipole interactions in their molecules. If we compare the difference in electronegativity, we'll see that it decreases compared to that of oxygen and hydrogen. Sulfur has an electronegativity of 2.5, hydrogen 2.1. The difference between those two is only 0.4. For selenium, the electronegativity is 2.4. For hydrogen, 2.1, and the difference is 0.3. As our difference in electronegativity increases, the polarity of our molecules increase. And as the polarity increases, the boiling point of that molecule will increase as well. Water is a liquid at room temperature and has a rather high boiling point, 100 degrees Celsius. This is due to its hydrogen bonds that it can form, the multiple hydrogen bonds that one molecule of water can have. H2S is a gas at room temperature, and it has a boiling point of negative 61 degrees Celsius. H2SE is also a gas at room temperature and has a boiling point of negative 40 degrees Celsius. As our dipole-dipole forces increase and eventually become hydrogen bonds if they're strong enough, the polarity of our molecules will increase. As the polarity increases, our boiling or melting points will also increase. The strength of the hydrogen bond gives water some very unusual and special properties. Most substances become more dense when they change from a liquid to a solid. This is not true with water. In liquid water, the molecules experience hydrogen bonds that will continually break and reform as the molecules move around. But when the water begins to freeze, the molecules will become locked in place, and each water molecule can participate in a maximum of 4 hydrogen bonds per molecule. So the one lone pair on the oxygen can participate in a hydrogen bond. The other lone pair on the oxygen can participate in another hydrogen bond. And then water has 2 hydrogens that can participate in their own hydrogen bonds with another water molecule. So a total of 4 hydrogen bonds per molecule. When liquid water freezes, the hydrogen bonding causes the resulting structure to occupy a larger volume than the same amount of liquid water. So ice will end up becoming less dense as a solid than it was as a liquid, allowing it to float. The hydrogen bonding within water also raises the boiling point substantially compared to other elements within the same family, such as H2S or H2SE, which were both gases at room temperature. Water's very strong hydrogen bonds allows it to be a liquid at room temperature, allowing life on Earth. Many molecules in biological systems, like proteins and nucleic acids, also contain NH and OH bonds. And the hydrogen bonding that can occur in these substances is one factor that determines their overall structure and biological function. The double helix seen in DNA is held together by 2 base pairs experiencing hydrogen bonding between them. Shown below are the molecular structures of 3 molecules. Which hydrogen atoms on these molecules can be involved in hydrogen bonding? We talked about for a hydrogen bond, we specifically have to have hydrogen bonded to oxygen, nitrogen, or to fluorine, 3 small electronegative atoms. So looking at the first structure on the left, this hydrogen is bonded directly to carbon, therefore it cannot participate in hydrogen bonding. This hydrogen, on the other hand, is bonded to oxygen, and it can participate in hydrogen bonding. Moving to the structure in the middle, this hydrogen is bonded to carbon, so it's not going to participate in hydrogen bonding. This hydrogen and this hydrogen, on the other hand, are both bonded directly to a nitrogen atom. Therefore, both of those hydrogens will be available to hydrogen bond. And in our third molecule on the right, these 2 hydrogens are bonded to carbon, so no hydrogen bonds, whereas this hydrogen in the upper right corner is bonded directly to a nitrogen, so that one will be involved in hydrogen bonding. The next type of intermolecular force that we're going to discuss is known as London dispersion forces, or LDFs for short. The attractions between polar molecules such as HCl are fairly easy to understand, but attractive forces will occur even between the particles of nonpolar substances. London dispersion forces are the weakest of the intermolecular forces. They occur between all types of molecules. They are in ionic compounds, covalent compounds. They exist in polar and nonpolar compounds. Specifically, though, they are the strongest type of intermolecular force in a nonpolar compound, whereas the strongest type in a polar compound could either be dipole-dipole or hydrogen bonding. London dispersion forces result from the movement of electrons within a molecule. The more electrons that a molecule has, the more movement those electrons can have, and therefore the stronger the London dispersion forces will be. If we look at a molecule of chlorine, chlorine is Cl2, it's a diatomic molecule, and the difference in electronegativity between 2 chlorine atoms is 0. Therefore, overall, this is a nonpolar molecule. So since it's nonpolar, it's not going to contain any London dispersion forces or any hydrogen bonds. But it still has some type of force holding it together. The forces that are between chlorine molecules are known as London dispersion forces. London dispersion forces are fairly weak intermolecular forces, but in certain molecules they can become substantial. Cl2 exists as a gas, but it can be condensed into a liquid. If it can be condensed into a liquid, there must be some intermolecular forces between the molecules to hold it together. We might imagine that if we draw the Lewis structure of Cl2, that because this is a nonpolar covalent bond, we say that the electrons are equally shared between each chlorine. We usually draw them right in the middle and assume that's where they stay. But electrons are always moving, so at any one moment the electrons contained within that covalent bond could shift to one side of the molecule. This shifting of electrons is what causes London dispersion forces in nonpolar molecules. Electrons are moving within our chlorine molecule, and if at any one moment the electrons shift from being evenly distributed to moving to one side of the molecule, an instantaneous dipole can form. Since it is a nonpolar molecule, it doesn't have a permanent dipole moment, but if the electrons become unevenly distributed, this instantaneous dipole or fleeting dipole moment can develop. One chlorine can develop a partial positive end, and the other chlorine can develop a partial negative end, where more of the electrons just happen to shift to at any moment in time. This shifting of electrons is what causes an instantaneous dipole in the first place. If one chlorine molecule develops an instantaneous dipole, it can induce another dipole in a neighboring molecule. So if we have one chlorine molecule that developed this instantaneous dipole at any moment where one side has a partial negative and one side has a partial positive, what's going to happen when it butts up to another nonpolar chlorine molecule where the electrons are evenly distributed? Well, that negative charge on the right-hand side is going to cause the neighboring molecule to develop a partial positive on the left-hand side, which would then cause the other chlorine in that molecule to develop another partial negative charge. So this instantaneous dipole will induce a dipole in the neighboring molecule. Therefore, in a sample of chlorine gas, we'll end up having many instantaneous and induced dipoles throughout. This interaction between the partial negative end and the partial positive end of two molecules is going to be a dipole, and this represents our London dispersion forces. It's a very short-lived attraction because the electrons are going to keep moving. The dipole will vanish as quickly as it forms. But when one dipole vanishes, in another moment, another one will form. Overall, there's going to be a net attraction. It'll be relatively weak because the attractive forces are turned off and on part of the time. These momentary dipole-dipole attractions are referred to as London dispersion forces. Let's compare two nonpolar diatomic molecules, Cl2 and Br2. Since they're both nonpolar, they're both going to experience London dispersion forces, but they have substantially different boiling points, so the intermolecular forces, or the strength of the London dispersion forces between them, must be fairly different. Chlorine is a gas at room temperature. Its boiling point is negative 35 degrees Celsius, whereas bromine is a liquid at room temperature. Its boiling point is 59 degrees Celsius. Bromine has many more electrons than chlorine does. Therefore, a molecule that has more electrons is going to have a greater movement of those electrons. It'll have stronger London dispersion forces between it. If it has stronger London dispersion forces, it's going to have a higher boiling point. Just because they're both nonpolar and they both contain London dispersion forces doesn't mean that we can't distinguish between them. The greater number of electrons will cause a greater movement and a stronger set of dipoles that form between the molecules. The number of atoms in a molecule will impact the strength of the London dispersion forces if the molecule is nonpolar. London dispersion forces will increase with the number of atoms. Molecular shape can also have an influence on London dispersion forces if the number of atoms and the type of atoms are identical. Let's look at 4 hydrocarbons to explain this. We have on the left N-pentane. Pentane has 5 carbons in it. Butane has 4 carbons in it. Isobutane also has 4 carbons in it. And propane, which has 3 carbons in it. The molecular formulas for each of these molecules are going to be slightly different, but we're just comparing the number of carbons to make some quick assumptions. Because when we have 5 carbons versus 3 carbons, the molecule that has a greater number of carbons is going to have stronger London dispersion forces. And if it has stronger London dispersion forces, that's going to impact the properties of the molecule, such as their boiling points. Pentane has a boiling point of 36 degrees Celsius. For butane, we have only 4 carbons in this molecule. Therefore, we should have weaker London dispersion forces than in pentane, and our boiling point should be a little bit less. For butane, the boiling point is negative 1 degrees Celsius. In isobutane, we have the exact same number of carbons and the exact same number of hydrogens in the molecule. Both molecules have a chemical formula of C4H10. So the number and type of atoms is not different, but the molecular shape of these two molecules is different. We'll talk about what's going on here in just a second. Isobutane compared to butane has a boiling point of negative 12 degrees Celsius, so less than that of butane. If everything else is the same, such as the molecular formula and the type of atoms, the geometry or the shape must be impacting the London dispersion forces in isobutane. Lastly, propane has a boiling point of negative 42 degrees Celsius. This one has the weakest intermolecular forces in the group because there's only 3 carbons within this molecule. Now, comparing the two structures in the middle that have 4 carbons each and 10 hydrogens each, we have one that has some branching. That would be the isobutane. Instead of it being a straight chain, one of these CH3 groups is moved, and it's created a branch point. This branching within the molecule affects the surface area overall. More branching will have less surface area compared to a straight chain molecule. And the less surface area that there is, the weaker those London dispersion forces in the molecule will be. A molecule with branching that has a lower surface area will have a more compact shape than a straight chain molecule. In the more compact molecule, the individual hydrogens on the neighboring molecules cannot interact as well as those on the chain-like molecules. Therefore, we end up seeing weaker London dispersion forces. Remember that all four of these molecules are nonpolar, so the only intermolecular forces that they experience are London dispersion forces, but different things can impact how strong those London dispersion forces are. Arrange the following in order of increasing boiling point. Before we decide which one's going to boil the highest and which one's going to boil the weakest, we should figure out what intermolecular forces are present and then rank them based upon their intermolecular forces. We have CCl4, CH4, CBr4, and CF4. What we first should notice about these four molecules is that they all have the same molecular shape or the same geometry. Each one of them is AX4, so their shape will be tetrahedral. Two molecules will lie within the plane and two will be pointing forward and backward. Also, they're all going to be nonpolar molecules. Because they have that symmetrical shape and the outer atoms on each one are identical, so for example, in carbon tetrachloride, all outer atoms are chloride. In methane, or CH4, all outer atoms are hydrogen. In carbon tetrabromide, we have 4 bromine atoms on the outside, and carbon tetrafluoride has 4 fluorine atoms. So therefore, that symmetry leads to them being nonpolar. If they're all nonpolar, the only types of intermolecular forces between a sample of the molecules will be London dispersion forces. Since they all have the same shape, we can't use geometry in order to determine which one is going to have the strongest London dispersion forces. But we can think about the size of the molecule or how many electrons it would bring to the dance. All of the central atoms are identical, each central atom being carbon. So if we compare the difference in the number of electrons of the outer atoms, we can make some assumptions about the London dispersion forces. If we look at the periodic table, the atomic number tells us the number of electrons that each atom will bring. Chlorine would bring 17 electrons. Hydrogen would bring 1 electron. 1 bromine atom would contribute 35 electrons. And 1 fluorine atom would contribute 9 electrons. Each of them have 4 of these, so it would really be this number times 4. But we're just trying to come up with a general trend. Since hydrogen would only bring 1 electron, this is going to be our smallest molecule and our least number of electrons. Bromine, on the other hand, each one would bring 35 electrons, so this is going to be our highest number of electrons. Recall that the London dispersion forces occur due to the movement of electrons within a molecule. The greater number of electrons, the greater the London dispersion forces will be within the molecule. So if we're ranking these in order of increasing boiling point, that would mean that CH4 would be our lowest boiling point because it has the weakest London dispersion forces, followed by CF4, followed by CCl4, and then the one with the highest boiling point would be CBr4 because it has the greatest London dispersion forces. The actual boiling points of each of these molecules: CCl4 boils at 77 degrees Celsius. CH4 boils at negative 162 degrees Celsius. CBr4 has a boiling point of 190 degrees Celsius. And CF4 has a boiling point of negative 128 degrees Celsius. So our trend that we derived based upon the intermolecular forces matches the literature value for the boiling points. The last type of intermolecular force that we'll study in this chapter are called ion-dipole forces. Ion-dipole forces occur from the interaction between an ion, this ion can be a positively or negatively charged ion, and the partial charges that we learned about that occur in polar molecules. For example, those partial charges could be dipole-dipole interactions, or they could be hydrogen bonding. Ion-dipole forces are moderately strong forces because we have partial charges on our polar molecule and we have full charges that will occur on our ions. For example, let's imagine that we have some salt, some ionic salt that breaks up into a cation and an anion in a solution of a polar solvent. How that polar solvent orients itself is going to be that the partial positive end of the polar molecule will surround or solvate the negatively charged anion. And the positively charged cation will be surrounded by the negatively charged end of the dipole from the polar molecule. The force between the cation or anion and the polar molecule would represent the ion-dipole interactions. These intermolecular forces are responsible for the formation of solutions. They allow ionic salts that are polar to dissolve in other solvents such as water or ethanol, which are also polar solvents as well. You may have heard the term likes dissolve likes. Ion-dipole forces are responsible for this. Usually in this class, when we're making solutions, our solvent has been water. Therefore, we said we made aqueous solutions. Water, we talked about, has hydrogen bonding as its strongest intermolecular force because we have hydrogen directly bonded to a small electronegative atom, which is oxygen. When ionic solids, such as sodium chloride, dissolve to give hydrated ions, the negatively charged chlorine atom will be surrounded by the partial positively charged hydrogen atoms in our water molecule. The positively charged sodium ion will be surrounded by the partial negative charge on the oxygen. Typically, we think about these ion-dipole forces being present in aqueous solutions, but sometimes they can persist into the solid state as well. Earlier in the semester, we talked about ionic compounds that form hydrates that have water as part of their molecular structure. That's due to the hydrogen bonds in the water being strong with the ion, and they stay there even in the solid state. Overall, ion-dipole forces are about 10% as strong as a covalent bond. So they are stronger than hydrogen bonds because we have the full charge on the ionic salt that is dissolved. The following gives a ranking from strongest to weakest of the 4 intermolecular forces we learned about. Ion-dipole being the strongest, followed by hydrogen bonding, then dipole-dipole interactions, with London dispersion forces being the weakest. They are only present in nonpolar molecules as their major intermolecular force. If we compare the strength of the intra and intermolecular forces, ionic and covalent bonding are intramolecular forces that are actually the bonds within molecules, and those are stronger than all 4 intermolecular forces. Ionic bonding contains full charges, positive and negative on the cation and anion, and that has the strongest interaction. Covalent bonds are sharing of electrons, and those are going to be the next. Then followed by the same ranking that we just saw, ion-dipole, hydrogen bonding, dipole-dipole, and London dispersion forces still being the weakest. What types of intermolecular forces are present in the following? NH3, aqueous KCl, H2S, methanol, and C2H6. First, we should draw the Lewis structure for each of these, and then based upon the structure, decide what intermolecular forces are present. In the structure for NH3, we have hydrogen bonded to a small, highly electronegative atom. Therefore, the strongest intermolecular forces present will be hydrogen bonding. London dispersion forces will also be present. London dispersion forces are in everything, but they're really only relevant when they're the strongest forces within a molecule. Aqueous potassium chloride. Potassium chloride is a solid, but if we dissolve it in water, it will break up into potassium ions and chloride anions. We have to remember that water is also a polar molecule, so we have ions and we have a polar molecule that will have strong hydrogen bonding. Therefore, we're going to have ion-dipole interactions. London dispersion forces will still also be present. H2S will have a bent shape with 2 lone pairs on sulfur. Sulfur will be bonded to each hydrogen atom. Just because we have hydrogen atoms doesn't mean that we actually have hydrogen bonding. Sulfur is not small enough or highly electronegative enough for it to be considered hydrogen bonding, but it is still a polar molecule. And since it's polar, the strongest intermolecular forces will be dipole-dipole interactions and London dispersion forces. Methanol, CH3OH, will have carbon bonded to 3 hydrogens, and then a 4th bond to oxygen, which is bonded to a hydrogen. Because we have an oxygen-hydrogen bond within methanol, the strongest intermolecular force present will be hydrogen bonding, along with its London dispersion forces. And lastly, C2H6. We're going to have 2 carbons singly bonded together, and each carbon will have a single bond to 3 hydrogen atoms. This is a hydrocarbon, and each carbon is tetrahedral. We learned that a CH bond is essentially nonpolar. Since this is a nonpolar molecule, the only intermolecular forces present will be London dispersion forces. It's important that you're able to draw the Lewis structure and then assess the polarity of the molecule and figure out what types of intermolecular forces would be present.